Hello people, how are you? High time for some more calculus meetings. So I'm calling this Calculus 3. If you want a private one-on-one session, email me at that address, jackpryunit@gmail.com. Okay, so far we have looked at the fundamentals of calculus, and we have looked at how calculus has two aspects, differentiation and integration, and that this fundamentally has to do with slope and this with area. And we're used to the idea of slope, and we're used to meeting it where it is a constant. So we've met it in connection with straight lines on the Cartesian plane. So if I take that line there, which is x equal to y, the slope is 1. It's 1 everywhere, it doesn't change. So if that's a mountain you're climbing, the nature of the climb will be the same all the time. In other words, every time you lift your foot up to go forward, you will go forward the same amount that you've lifted it, which is why the slope is 1. Okay, the rise over the run. The rise over the run will always be the same. In other words, no matter what kind of a triangle I draw to this line, like so, a right angled triangle, horizontal, vertical, right angled triangle, no matter what kind of triangle I draw, this length here and this length here will always be the same. Okay, that's for that line. There are lots of other lines where different relationships between the rise and the run prevail, but again, they will be unchanging for the given line. So if I draw triangles against this of any kind, like so or so, for this straight line here, that length over that length will be the same as that length over that length. Yeah? But calculus is a tool that is enormously useful, and in this scenario it applies to situations, and I'm just talking about differentiation at this point, which is concerned with slope. So calculus, when it comes to dealing with slope, it's really interesting and really useful in a scenario where the slope is not a constant. So we looked at the function after the straight lines, all the straight lines. This is one of the simplest functions you will meet. That's not a straight line. So it's y equal to x squared. Okay. And as we can see here, the rise over the run, there we are, climbing up. The rise over the run will change as we go up along that curve. If we look at it down here, so down here, it's that, almost 1 actually, right there. But if we go up here, it's that. So the relationship between the rise and the run keeps on getting bigger. All right. If we're climbing up there, it's a mountain, hard mountain to climb. All right. So, and the beauty of differentiation here is that it establishes a relationship between the variable, which is x down here, and slope as a varying quantity as well. So, we now then have two functions. So we have y equal to x squared, and then we have dy dx equal to 2x. Okay, so for this function, the first primary function here relates progress along this line here to progress along this line here for this particular curve. Okay, just one sec. Sorry, there's my maths problems down there on the computer. Okay, and we also looked at integration, which is concerned with area. And again, if we integrate here, it's in the other direction, if you like. So this is the notation here. Integral of y dx is equal to 3x squared. Sorry, what am I saying? Okay, it's x cubed over 3. Okay, and those are the three functions that pertain to this particular curve. The central one here relates progress along this line to progress along this line. The red one here relates the change in slope to progress along this line here. And the integral up here relates progress along this line to the area under that curve as we progress. Okay, so that's a little recap of differentiation and integration in the general context of calculus. Now, my goal today is to look at some simple enough differentiations which, where are we here? Page 25. All right. 25. All right, so here we are. So there's a list of standard differentiations here in this wonderful text, which if you live in Ireland, you should kind of sleep with that under your pillow at night. If you kind of care about maths at all, which I think you should. Anyway, I love maths. Okay, anyway, so we're just dealing with the very first rule there, which deals with the function y equal to x to the n. And the problems I'm going to look at today relate entirely to that one rule. So put it up over here, y is equal to x to the n, and according to our tables, if we differentiate that, we'll get dy dx equals n times x to the n minus 1, like so. Okay. The last in Calculus 2, we looked at how to differentiate from what we call first principles. And basically, differentiating from what we call first principles is kind of a more abstract way of using the simple slope equation, which is y2 minus y1, which is the rise, over x2 minus x1, which is the run, as we go from one point to another along the curve. Now, I may come back to that at some point, but for now, today, before we move on to what's called the chain rule, which is like the most important rule in all of calculus. So if you understand the chain rule, you understand differentiation, basically. That shall be in calculus 4. Okay, sip of coffee. Cheers. All right, so let me just look at my problems here for a sec. All right. I shall bring this over here. All the better to look at it. So, all right, so first standard thing I'm just going to look at it is some very standard problems of the form y equal to x to the n. So y equal to x cubed. If I differentiate this, remember, it becomes n times x to the n minus 1. Okay? And anything that we encounter of that kind will follow that pattern. Okay, so y equal to x cubed will become, you guessed it, dy dx is equal to 3x squared, like so. And that's fine. If there's a number in front of it, what happens there? So let's say we have y equal to 4 times x cubed. We do exactly the same thing, because in this scenario the constant coefficient for the function, in this case 4, doesn't really come into play at all. So we still do as we did up here, dy dx is equal to 12x squared. Okay, so that's 4 by 3x squared, like so. If you can see that, all right. And okay, what else do we have here? Okay, so we generally have x, or we very simply have y equal to x. We've already looked at this function in a simpler context. It's basically the diagonal straight line there that kind of dissects the plane. And we looked earlier and we saw by more traditional and simple means that the slope of this is 1. But if we differentiate this, so I'm going to write this now as y equal to x to the 1, okay? And right, so we'll differentiate that in exactly the same way then. Dy dx is equal to 1 times x to the 1 minus 1. So as we all know, 1 minus 1 is 0, and x to the power of 0 is, anyone? It's 1, basically. Okay. Now, as far as indices go, this is something, I'll be doing a section later on logs and indices, and as far as that goes, this is something that we will be looking at, okay? And there are other bits and pieces we are now going to encounter, so okay, so if we're to differentiate a constant, okay, so what? Okay. All right, so let's say we have this here. So it's just 5, y equal to 5. And if I differentiate that, okay, yeah, can I differentiate it is a question, or do I need to differentiate it? Because basically I'm concerned with the slope of it. So let's look at what y equal to 5 is, okay? So I'm just going to draw my x and y axis here on the Cartesian plane. And I'm just going to mark up along here on the y-axis the numbers 1, 2, 3, 4, 5. So the line y equal to 5 is this one here, along there like so. Okay. And basically the slope of that is 0 because it's flat. Okay, it's parallel to the x-axis, which is our definition of flat ground in this scenario. And y equal to 5 implies dy dx equal to 0. Is there any way of doing that according to the rules? I'm not sure, but I will have a think about that. But you understand that anyway. Okay. And it doesn't vary with x at all, actually. Yeah. Like, so no matter where we go on this line, y will always be 5. Okay, whatever it might be, 1, 5, 2, 5, etc. Okay, that's that. What else do we have here? All right, so we get into things like 1 over x squared. So let's look at those. So if we have y equal to 1 over x, like so, yeah. And if we want to differentiate that, okay, I will write it, I have to write it first of all, so we'll say write in the form x to the n. All right, so how do I do that? Well, basically 1 over x, like so, can be written as x to the minus 1, like that, because the power of the x here is 1, as we know. Okay. And now I can just, oh, all right, so this is another indices thing that we need to look at down the line. Why are these the same thing? That one there. Very simple reason, as it happens. So then when I differentiate that, straightforward enough, we get dy dx equals minus x to the minus 1, which is equal to minus x to the minus 2, which is equal to minus 1 over x squared. Okay, minus 1 over x squared. All right. And there may be more that needs to be talked about with this. As you can see, the slope is always negative, yeah. And just, I mean, very briefly, if I were to plot that graph, it would actually look something like that there and that here. So, and this is what's called an asymptote. Is it an asymptote? It's an asymptote, I think. Anyway, 1 over x is not defined on the y-axis, because on the y-axis x is 0 and 1 over 0. If you punch that into your calculator there, it will pop up an error sign. Okay, so basically the smaller x gets here, the bigger y gets. Okay, and it goes off up here to infinity. And something similar down here, but you will see that always the slope is going, if you like, from that quadrant to that quadrant. No matter where we go on those two curves, the slope will always be negative. It's always a hill you're going down, in other words. Okay, you're walking down here, down, 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 or here, down, 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 down. Okay. That's that. I'm just going to clear this board if you don't mind. So I rubbed out my Calculus 3. What am I to do now? Okay, Calculus 3. All right, so we look at a few more bits and pieces here. Anything under the line like that. So 1 over x squared we rewrite as x to the power of -2, and dy dx becomes -2x to the power of -3, which is -2 over x cubed, like so. All right, we will move on to, let's see. Okay, back. All right, so and again, the addition of constants into these scenarios make no difference whatever. So for example, if we had 3 over x squared, y equal to we proceed in exactly the same way, so it would be equal to 3x to the -2, and again we differentiate as if this were not here. We don't discard it, but we differentiate as if it were not here, so we get dy dx is equal to 3 by -2x to the -3, which is -6 all over x cubed. Okay? What next? All right. So, okay. That's that. Square root, our old friend. If I were to ask you to define square root for me, and if you were to kind of intuitively think about that, what would you come up with? So, if we have y is equal to the square root of x, now, again, this is a problem for the section on indices, but we write that, or can write that, as x to the power of a half. Now, again, this is something I'll be looking into. But again, if we are to differentiate that, we proceed in exactly the same way. Dy dx is equal to a half x to the power of a half minus 1, and that's equal to a half x to the power of minus a half, which is equal to 1 over 2x to the half, which is equal to 1 over 2 root x. Like so, yeah. And basically that then will apply to any fraction index, if you like, or indice. Is that the right word? Okay, anyway, you know what I'm talking about. So we will now look at let's say y equal to x to the power of a third. Okay, and that's the third root of x. Okay, again, think about what that is. What does that mean, the third root of x? But if we differentiate it, as complex as this might be, there is no difference at all. Okay, dy dx is equal to a third x to the power of a third minus 1. Okay, and that becomes that becomes 1 over 3x to the power of 2/3. All right. Okay, so in this particular book that I'm looking at here, there are a bunch of other problems, but they all involve combinations of this kind of thing. So, and basically in a scenario where you have a bunch of plus signs or minus signs separating the elements of a function, and I will give you an example presently. We just hold on to the plus signs and the minus signs, and we just differentiate in the normal manner. Now, again, to stress that we are still only dealing with this rule here. The first rule in your mathematical tables there. So dy dx is equal to n times x to the n minus 1. Yeah. So to give you an example, we have what? Let's say we have something like x squared minus 5 over x. And again, that's our y. So our dy dx is equal to 2x to the power of 1. This comes above the line, so we have minus 5x to the minus 1. That gives us 5x to the minus 2, which is 5 over x squared. So plus 5 over x squared. So again, because there's a minus or a plus between the items here, we simply just differentiate each item in turn, yeah, and hold on to the minus and plus signs as I have done here. This minus has actually become a plus in the process, okay? And if you look in your books, the differentiation, the first exercise is on differentiation by rule. You will come across lots of problems of that kind. Now there's one last one I'm going to look at today, and let's say we have a function of the form x minus 2 cubed. Okay, in fact, let's spice it up a bit. I'm going to say it's x squared minus 2. Sorry, let's say squared. Okay, so I'm going to multiply that out. As I look at it, I can't differentiate it as it is, right? But I can multiply it out, so we will get x to the 4 minus 4x squared plus 4, like so. Yeah? That's correct, isn't it? So now we can differentiate that by taking each of these items in turn. We have minuses and pluses separating them. So our dy dx is equal to 4x cubed minus 8x, and the 4 goes to 0. Yeah? And that's that. However, and we can always, in theory anyway, do that. But let's say we had y equal to x squared minus 2 to the 10, like that. Now, technically, we could multiply that out. We'd be at it all day long. Maybe we could use a computer. I don't know. We'd be at it for a long time anyway, and the chances of making a mistake are huge. So this leads us into the excitement, I know, is too much. What we call the chain rule. And the chain rule not only is of enormous relevance, but if you understand the chain rule, you basically understand differentiation. Yeah. That would be my take on it, and I have a very particular way of teaching it, which I certainly find useful as far as understanding goes. So we'll look at that in the next section. As I say, if you hit the subscribe button down there, please, just do it. Okay. And private session, email Jack unit at gmail.com, or just give me a call actually on 0035386066270. All right, just one sec, sorry. 705, like so. Okay, we shall leave it there for today. Don't forget to subscribe and like, and we will talk again. Well, I'll talk. Okay, I'll be happy to talk again soon. All right, take care. Bye.